Okay, so last time we looked at perpendicular axis and we saw that perpendicular axes were related to each other by this relationship here. We said that if you have two axes that are perpendicular to each other within a plane, then the moment of inertia of a third axis that's perpendicular to the plane of containing the other two axes will be the sum of the moment of inertias of those two axes. Right? So Iz equals Ix plus Iy. It's a lot shorter when we just use the math. Okay, so anyway, now we want to look at if there's a relationship between axes that are parallel to each other. And particularly, and there is a relationship, a specific relationship between axes that are parallel. But it is important to note that one of those axes, within that relationship, one of those axes must pass through the center of mass of the object. So let's go ahead and establish that relationship right now. So suppose that we know the moment of inertia about a line L that goes through the center of mass of a particular object. And we wanted to determine the moment of inertia about another line that does not go through the center of mass but is parallel to that first line. So LO, for example, L subscript O is parallel to L. We want to determine the moment of inertia. I'm going to set up my diagram as such. So I have the centroid located here, and my line L is coming out of the plane of the board, and that's affiliated with axis X prime and Y prime. Then I have the line LO coming out of the plane of the board here, perpendicular to the plane of the board as well. And the axes affiliated with LO are X and Y. Okay. So I can say the moment of inertia about line L sub O would be given by the integral of r squared dm. Here's my r, here's my dm element, and there's my, remember my L sub O line is coming out of the plane right here, and oops, let's go back. So, and my r is a perpendicular distance from that line. Remember, the line is perpendicular to the plane of the board, so r must be perpendicular to that line because r is in the plane of the board, right? So I have my perpendicular distance from that line to my element dm, integral of r squared dm. And of course, we know from Pythagoras' theorem, r squared is x squared plus y squared. So I could write it as such, right? Now, if you look at line L that is passing through the centroid, I can orient my position of line L passing through the centroid by these relationships here. If I look at my x prime axis, I see that my x distance, which is, let's say, from here coming all the way out to where the element is located, would have to be some dx plus my x prime distance, dx being the distance from the y to the y prime axis. So remember, the x distance to point M would come from the y-axis all the way out there. So clearly x must be equal to dx plus my x prime distance, which comes from the y prime distance to dm, right? And similarly, we can say y is equal to y prime plus dm, dy. Now the moment of inertia about that line LO, L sub O that we talked about earlier, well, I'm going to plug in these expressions for that moment of inertia, the expressions I have here and here for x and y. So I get x prime squared plus y prime squared. And you know, once you expand, you're going to have a 2d x prime, 2dx x prime term, a 2dy y prime term, and a dx squared and a dy squared term, dy squared term. Now, actually, we can see a couple things here, because if I recall what the definition of the center of mass is, the definition of the center of mass of an object, it's given by the integral of x dm or x prime dm divided by the integral dm, right? Similar for my y prime. But for when for my line L, my line L is going through the center of mass. My line L is going through the center of mass. So therefore, if I'm using my x prime and y prime axis, the coordinates of my center of mass, x bar and y bar, must be the origin, which would be 0 and 0 for my x and 0 for my y. So if x bar is 0, then this integral in the numerator is 0, and if y bar is 0, same thing, this integral here is 0. So I see my integral x prime dm, my integral y prime dm, those go to 0, because again, what my x prime and y prime axis, the origin is at the center of mass. Now how about this dx squared plus dy squared term? Well, if I look at dx squared and dy squared, I can see here that dx squared plus dy squared from Pythagoras' theorem would give me d squared, right? Dx squared would be here, dy squared, well, dx would be here, sorry, dy would be there, and d would be the hypotenuse of that right triangle. So that's just d squared here. So dx squared plus dy squared, we know that's d squared. Now what's the integral of dm? Well, the integral of dm, that's the integral of all the elemental masses over the complete mass of the object. So the integral of dm must be m. So this is where this md squared here term comes from here. Right? Remember, dx squared plus dy squared is equal to d squared. D squared is not changing. D squared is constant. So d squared is not changing with mass. We just have d as the distance between O and the center of mass. Now how about integral x prime squared plus y prime squared dm? Well, if we look here, we know x prime would be the x distance out to dm, y prime would be the y distance up to dm, and that's just r squared, or r prime squared, excuse me. So that's just a moment of inertia about the z-axis, or about the perpendicular axis coming through the center of mass. So that's what this term here is what I'm going to call I, which is the moment of inertia about an axis through the center of mass. So generally, we can relate parallel axis by this expression, where one of the axis is about, one of the moments of inertias is about an axis through the center of mass, and the other one here is about the moment of inertia about an axis parallel to this one. So we call this the parallel axis theorem. Okay. Alright, so moving on quickly to an example. I have two homogeneous slender bars, each of length L mass M. Okay, and we're given a cross-sectional area A, and they're welded together. And we want to use integration to determine the moment of inertia of this object about L sub O, which is an axis perpendicular to the bars at the end here. So this is a 1D type scenario. Right? This is a 1D scenario. Right? One length is much more significant than the other two. Well, here's what we're going to do. We're going to do what we did before with the 1D scenario, where we define an element, an elemental length, or actually we define an elemental mass and associate with it an elemental length. In the first case we looked at was dr, so now I'm going to call it dx, just because I'm along the x-axis. Alright, and I can introduce two elements here because I have two bars. I have one is horizontal, the other one is vertical. So here I can introduce another element dm, some elemental length dy, because this one is vertical, right? And then we can move forward with those sort of basic choices. Alright, so now with my element here, well, I know the moment of inertia about some axis O is going to be the integral of r squared dm. Again, I know dm could be written as what? The density times the volume. Now we have an elemental mass, so I'm going to have what? dm equals rho, the density, multiplied by the elemental volume, which would be the area times the elemental length, a dx. So I plug that in here. And what would be my r? What's r again? It's the perpendicular distance from the axis to the elemental mass. So in this case, my r distance, the axis we're talking about here, is coming out the plane, perpendicular to the plane, coming out at O. So the r distance must be x, right? So that's where this x squared terms comes from, right? Integrate all of this. Remember, my rho a doesn't change, so I have x squared. I'm integrating from 0 to L. Why is that? Well, just take a look at the figure here, right? My element is, my axis is starting at O, is passing through O, and my element is going to traverse the entire length of the bar because we want to know the moment of inertia about the line through O. So my limits will be 0 and L. Now we can do something very similar for this vertical axis. All right, I have my dm mass element, my dy. I know it's rho a. My dm would be density times volume. My volume would be a dy, right? Area times elemental length. What about my r squared term in this case for this vertical bar? Well, I'm looking at this axis O, therefore my r, or a line that's perpendicular to O, so my r is perpendicular to that line coming out the plane, right? Perpendicular to the plane and going to the elemental mass. Now, since we're doing dy, we want everything in terms of y. So if we look at our diagram here, we could express r in terms of the length of this bar and y, right? I can see that r squared equals L squared, the length of that bar, which is not going to change, plus y squared, right? And of course, as dm goes up and down, y will change. So my final term looks something like this. See, I have the y in the y term only, that's varying with the dy. So I can do my integration with the limits 0 and L, and I end up with this expression here. Now guess what? Moment of inertia is additive. It's additive as long as we're talking about the same axis. So if I know the moment of inertia of this piece of the bar about the axis through O, and I know the moment of inertia of this piece 1 of this bar, or bar 1, let's say, about an axis, same axis through O, to find the moment of inertia of the combined pieces, I can simply sum the two moment of inertias that I had previously determined. So that's what happens here. That's what we're doing here. So the 1/3 ml squared will be the moment of inertia of the horizontal bar, while the 4/3 ml squared is the moment of inertia of the vertical bar about the same axis, again axis passing through O and perpendicular to the plane of the paper.